Hello, everybody, and welcome to Discrete Math lecture number 6. Today we're going to talk about quantifiers and propositional functions. We'll get to propositional functions first. A propositional function is a function that accepts as input one value or one object and yields as output exactly one of the two values, either true or false. And this bit about me defining the input as one value or one object, I'll tell you in about 5 minutes why I might want to refer to the input as an object rather than a value. Let's look at an example. Here our propositional function p of x involves the statement x is greater than or equal to 3, where x is a variable. What happens if we take 4 and plug it into our propositional function for x? Well, in that case, we're plugging 4 in for x into this statement, and this statement is either going to be true or false. Is 4 greater than or equal to 3? Sure is. So when x equals 4, our propositional function is equal to true, or t. Now let's look at another case. Let's suppose that x equals 2. We plug 2 in our function for x, and if we plug 2 in for x, is it true that 2 is greater than or equal to 3? No, it is not. So here, the propositional function yields the value of false. In the first case, we plug in the value 4, and the function gives us as output the value of true. In the second case, we plug in the value of 2, and we get as output the value false. And for all real numbers x, this propositional function will either yield true or false, because for all real numbers x, either x is greater than or equal to 3, or it's not. So either the statement is true or it's false. Now let's look at another example. Okay, here's an example of a propositional function that might justify me using the word object instead of value as the input. Here for input, we plug in not one real number, but an ordered pair of real numbers. And we apply this to the statement x is greater than y. For every pair of real numbers, x and y, either this statement is true or it's false. So let's look at the first case. That we take the ordered pair x equal 1, y equal 2, and plug it into the function. So is it true that 1 is greater than 2? No, it's not. So when we plug the ordered pair into this propositional function, we get the output of false. Now let's try inputting a different object or ordered pair. This time we're going to plug in x equal 4, y equal 3. And when we plug this ordered pair into our function, is it true that the statement 4 is greater than 3 is true? It sure is. So when we plug the ordered pair 4, 3 into our propositional function, our function yields the output of true. And for every pair of real numbers, x, y, this propositional function will give us exactly one output, either false or true. Next, we define a quantifier. A quantifier is a symbol or a phrase that tells us how many objects or for how many objects a proposition is true, or for which objects a proposition is true. A quantifier is a symbol or a phrase that tells us for how many objects a proposition is true, or for which objects a proposition is true. The first quantifier that we'll look at is called the universal quantifier. In other words, it states that something is true for all objects in the universe, whatever the universe happens to be. So the universal quantifier is denoted this way. It's an upside down A. And I think that's the symbol that's used because A is the first letter in all. So the universal quantifier, upside down A, is expressed using phrases such as all, or for all, or each, or for each, or every, or for every. So these are the different phrases that are used to express the universal quantifier in words. Now let's look at an example. Suppose that we have a propositional function on x, where x is a real number, and the propositional function is based on the proposition x is greater than or equal to 3. Well, we could state, using the universal quantifier, that for all x greater than or equal to 3, the proposition is true. So this statement symbolically could be represented in words as, for all values of x greater than or equal to 3, p of x is true. Or for each value of x greater than or equal to 3, p of x is true, and so forth. Let's consider another example. Consider the proposition p of x, which is based on the statement x squared is less than 9, where x is a real number. We can render this proposition as follows. For all x such that x is between -3 and +3, our proposition p of x is true. Or for each x such that x is between -3 and 3, our proposition is true. Or for every x such that x is between -3 and +3, p of x equals true. All three of these statements say the same thing. We're just using slightly different versions of the universal quantifier. This one says for all x, this one says for each x, this one says for every x. They mean the same thing. The words are different, but they mean the same thing. And all three of these statements can be written using the universal quantifier symbol, the upside down A. And we do it in two ways. For all x such that x is between -3 and +3, p of x equals true. Or for all x such that x is between -3 and +3, p of x is true. Now the difference in these two renderings, these two symbolic renderings, is that one we have a colon here, and here we have sort of a backwards E or something. Both of these are ways of symbolically expressing the English phrase such that. For all x such that x is between -3 and +3, p of x is true. For all x such that x is between -3 and +3, p of x is true. Now let's take a look at another quantifier. Let's continue with the existential quantifier. The existential quantifier is denoted by the symbol, and this is just a backwards capital E, and is expressed by the phrases there exists, there is, there are some, for at least one. The existential operator is used to indicate that a propositional function, p of x, is true for at least one value x, or one object x. So this backwards E is appropriate because we associate the E with the first letter in the word exists. So we look at this and we say, there exists at least one, or there are some, or there exists some, but always at least one. Now let's look at some statements written symbolically and using phrases instead of symbols. Let's consider this statement. Consider the propositional function p of x based on the statement x is a bird that cannot fly. Now we can express this using phrases there exists a bird that cannot fly. There exists at least one bird that cannot fly. Some birds cannot fly. And essentially, they all have the same rendering symbolically. There exists a bird such that p of x is true. The bird cannot fly. There exists at least one bird. Well, we render that the same way. There exists p of x such that the bird cannot fly. P of x is true. And is that showing up on the board? Barely. Let me see if I can get a better marker. Ooh, this one looks good. Okay, I think we can use that one. And the last one, some birds, well, you know what? We represent this, the whoops, 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 whoops. This is not right. Why didn't one of you raise your hands and tell me? There exists at least one bird. In other words, there exists at least one x, such that p of x is true. And I was about to cut my throat here, too. Some birds, that is, some x, there exists an x, cannot fly, p of x. So symbolically, we represent all of these the same way using the existential operator. there exists an x such that p of x is true. Or we could say there exists an x such that p of x is true. And you know, in our text, a lot of times our author doesn't use either of these. Our author doesn't use anything at all. We have to supply the phrase such that. In our book, they may write it this way. There exists an x, nothing right here. There exists an x, p of x is true. We have to supply the phrase such that. So if we see something like this in the book with no colon, no backward z, we may have to supply the phrase such that. Now let's do a few more of these things. Given the propositional function p of x based on the statement x squared equals 10, where x is a real number, we're asked, given the statement there exists an x such that p of x is true, or without the colon, there exists an x such that p of x is true. Render the phrase without using symbols. Okay. Well, we can do that. One way we could render this part is there exists a real number x such that x squared equals 10. That's one way to do it. Another way, we could say there exists at least one real number x such that x squared equals 10. And now can we do this without using the word exists? Some real numbers x are such that x squared equals 10. Some real numbers x. And yeah, let me say it this way. Some real numbers x are such that x squared equals 10. Now let's do one more of these. And let's consider this. We have the propositional function p of x. All x are rich, where x is a doctor. And we want to render the statement for all x, p of x is true. Or without the comma, for all x, p of x is true. Now, how are we going to do this? X is a doctor, so for all doctors, x is rich, or for all doctors, doctor is rich, or just all doctors are rich. Or every doctor is rich. I think these would be the two best renderings of this example. Let me do one where I use a mathematical expression and translate it into words. Okay, this one may seem a little bit more natural than the one we did before. We have the proposition P of x, which is based on the statement x squared is greater than or equal to 0, and x is a real number. So we have the proposition for all x, or for every x, or for each x, P of x is true. So here's how I would do this without using the symbols. For all x, or for all real numbers x, x squared is greater than or equal to 0. And I could say for each real number x, x squared is greater than or equal to 0. Or I could say for every real number x, x squared is greater than or equal to 0. Before we get into determining exactly what circumstances or under exactly what circumstances a propositional function would be true or false, let's consider something, a term that our author uses. Suppose we have a propositional function P of x. The author defines expressions such as for each x, P of x is true, or there exists an x such that Q of x is true, or for all x, P of x is true, there exists an x such that Q of x is true, there exists an x such that Q of x is true. These 5 expressions, this one, this one, this one, this one, this one, our author defines expressions like these to be quantifications. So a quantification is a propositional function, P of x, preceded by a quantifier, either for each x or there exists an x, and maybe some other quantifiers that we have not yet talked about. But what our author calls a quantification is a propositional function preceded by a quantifier. The negation of quantifications. To correctly negate a quantification, we have to consider what must necessarily be true in order for the quantification to be false. What must necessarily be true in order for the quantification to be false. And consider this quantification. For all x, P of x is true, where P of x is the propositional function x can fly, and x is a bird. We can therefore render the quantification for all x, P of x is true as for all birds x, x can fly. Or even more simply, all birds can fly. Now, all birds can fly. Is that statement true or is it false? And we say, well, that statement's false. And I say, well, how do you know? And you say, well, penguins are birds and they can't fly. So in order to make this statement false, did we have to establish that every single bird is incapable of flight? Or did we just have to show that there exists at least one bird that can't fly? We looked at this and said, all birds can fly? Oh, that's false. How do we know? Well, a penguin's a bird and a penguin can't fly. To negate this statement, all we had to do was show that this statement was false for one bird. So when we have the quantification for all x, p of x is true, the negation of this is going to be there exists an x such that p of x is not true. That's the negation of it. And we're going to write this down. What we've just established is that the negation of the quantification for all x, p of x is true, is the quantification there exists an x such that p of x is false, or there exists an x such that it is not true that p of x is true, or there exists an x such that p of x is false, not using any colon here. So the negation of the quantification for all x, p of x is true is logically equivalent to the quantification there exists an x such that p of x is false. The negation of for all x, p of x is true is logically equivalent to there exists an x such that p of x is false. Summing this all up, we say that the quantification for all x, p of x is true. This quantification is true exactly when p of x is true for every value of x. Thus, the quantification for all x, p of x is false exactly when there exists an x such that p of x is false. The quantification for all x, p of x is false exactly when there exists at least one value of x such that p of x is false. And we call such a value of x a counterexample. And before I go any further, let's finish this. I'll add my statement at the bottom. Hence, the way to show that the quantification for all x, p of x is false is to provide a counterexample. A single value of x such that p of x is false. And this is very appropriate. If no such value of x exists, then the quantification for all x, p of x is true. So if there does not exist a value of x that makes p of x false, then the quantification for all x, p of x, is true. So this is an important thing to remember. We have this quantification for all x, p of x. If we can't find, or if there does not exist a single value of x to make this thing false, then this thing is true automatically. Now let's look at the negation of the other quantification. There exists an x such that p of x. To find the negation of the quantification, there exists an x such that p of x is true, or without the colon, there exists an x such that p of x is true. Now, we have to ask ourselves, what must necessarily be true in order for this quantification, there exists an x such that p of x, what must necessarily be true in order for this quantification to be false? And usually when we ask a question, there's a question mark at the end of the sentence. Now let's consider an example. Let p of x be the propositional function x can fly. And suppose that x is a bird. So the quantification, there exists an x such that p of x is true, can be rendered, there exists a bird that can fly. Or there exists at least one bird that can fly. Or it can be rendered, some birds can fly. Now, how do I negate this? Do I negate this by saying, well, some birds can't fly? Is that the negation? And we say, some birds can't fly. Penguins can't fly. Penguins can't fly. But does that make this statement false? Does the fact that penguins are birds and penguins can't fly make this statement false? There exists a bird that can fly. No. Just because one bird can't fly doesn't mean that other birds can't fly. So just because this statement is false for one x doesn't mean that just because our proposition is false for one x doesn't mean that this quantification is false. This quantification can be true even though for some x this propositional function is false. Now think about this. Some birds can fly, or there exists a bird that can fly. What would have to be true for these statements to be false? Well, we could say some birds cannot fly. But wait a minute, does that make this false? Penguins can't fly, but that doesn't mean that this statement is false. Some birds can fly, some birds can't fly. Both of those statements are true. So the way to make this statement false is not to say that some can't, or there exists one that can't fly. What absolutely has to be true to make this statement, some birds can fly, false? It would have to be true that no birds could fly. No birds can fly. So for all x, p of x is false. So for all birds X, it is false that X can fly. For all X, P of X is false. This is how we negate a quantification that uses the existential operator. For all X, P of X is false. Now, there is another way that we could do this, and that's to negate the existential operator. I'll give two ways of negating this. This negation is rendered this way. There does not exist an X such that P of X. So there are actually two ways that we could negate this quantification. And I will write these down in just a second. So symbolically, the negation of the quantification, there exists an X such that P of X, is for all X, P of X is false. And there's an equivalent way of doing this. The negation of the quantification, there exists an X such that P of X, can also be written as there does not exist an X such that P of X. So there are two ways of doing that. Now I'd like to give one more quantification. And that has to do with the uniqueness quantification. There's one more quantifier that we need to see. It's the uniqueness quantifier. And it's denoted with the backward E followed by an exclamation mark. The backward E, we're sort of familiar with that. The backward E says there exists. The exclamation mark after it tells us that the existence is unique. In other words, there exists exactly one, no more, no less. So this is a logical expression equivalent to the phrases there exists a unique or there exists exactly one. And just to give an example where this would fit in, let's consider the propositional function P of X, where the proposition is 1 over X is undefined, and X is a real number. Then we can write there exists a unique X such that P of X is true. And this is true. In words, there exists a unique real number x such that 1 over x is undefined. So here's our p of x. And all of this is just, there exists a unique x. And this statement is true. X equals 0 is that unique number that we divide by x and we get something that's undefined. For every other real number, this expression is defined. So we could say there exists an x such that p of x, and that would be true. But this would imply that maybe there exists more than one x such that p of x is true. If we want to be precise, and in this case we can, we'll say there exists exactly one real number x such that 1 over x is undefined.